to be given by one of our online participants, Jen McGarry from NASA GSFC. She's going to tell us about the current status of plans for tests and developments of the first NASA SGSLR system. Jen?
Good morning. I don't think my slides are quite up yet. At least I can't see them.
We thought you were giving your slides. Hold on a second.
Okay, great. Good morning. As Claudia said, I'm going to be talking about SGSLR. My co-authors are Evan Hoffman and Stephen Merkowitz from NASA, Scott Wetzel, Bud Donovan, and Julie Horvath from KBR. Sorry. Our first system will be going to Ny-Ålesund in Svalbard, Norway. We'd like to thank our colleagues from the Norwegian Mapping Authority who have been supporting the SGSLR development and deployment efforts. We also want to acknowledge that we are not the only ones, the authors are not the only ones working on this. We have a team back home, and we want to thank all of our colleagues who are working to make this new SLR system a reality. This is the basic outline of my talk. I want to mention that there are other presentations at the workshop related to this talk. One of them follows mine. Garl will be presenting the Ny-Ålesund site and SGSLR deployment there. Evan Hoffman's going to be talking on Friday about laser safety at these new stations. And then there are two posters, one by Christopher Clark on the analysis of the SGSLR receiver testing, and one by Ulla Klingen on laser safety at Ny-Ålesund. We're actually building the first three SGSLR network systems at the same time, although obviously our focus is mostly on the first system at Ny-Ålesund. This is a simplified block diagram of SGSLR, which has been shown at previous workshops. There are basically 9 systems, subsystems, and the slides that follow, I'll be talking about the status of each. The first one is the gimbal and telescope assembly. We first had a gimbal without a telescope. We had a mass simulator on it. It had a 6-inch mirror that took the light down through the Coude path down into the optical bench. We were able to perform tests, star calibrations, and sunlit satellite tracks with good results to give us good confidence about the gimbal. As soon as the telescope was ready, it was mated with a gimbal, and they became GTA number 1. That system successfully completed factory acceptance testing at the manufacturer, which is Cobham, at their Lansdale, Pennsylvania facility. The middle picture is that, and by the way, the picture on the left is the gimbal and mass simulator. The gray box is the mass simulator. GTA number 1 is now at Goddard. The picture on the right shows it in the dome at GGAO. And we are in the middle of site acceptance testing. GTA number 2 for Ny-Ålesund is currently going through factory acceptance test in Lansdale. The receiver that we will be using is the Sigma Space pixelated detector. We've discussed, we've had some talks on this in previous workshops. We're able to do testing on both single and multi-cube targets using the 1.2 meter telescope facility at Goddard, which is separate from the SGSLR facility. You can see the setup in the lab on the lower left. And the analysis of an hour-long ground test, stability test, is shown on the right. The lowest, the red plot at the bottom of the plot, is shows the results from from a single cube ground ranging, which is very stable with a standard deviation of much, much less than a millimeter. Our primary aircraft avoidance technique is, or system is, the KBR's laser hazard reduction system. We will be using this at GGAO and also at McDonald Observatory. We, however, cannot use this at Neolison due to the restrictions on RF transmission. So NMA will be and is in the process of developing an ADSB for aircraft avoidance at Neolison. And so we have to mate the two parts of the laser safety systems, the NMA part and the part that remains at SGSLR. And the document you see on the lower left is the version 1 of the interface control document between our two systems. The time and frequency units are all built. These were built, designed and built by with mostly COTS components by KBR. The GGAO version, which is installed in the SGSLR shelter, is shown in this picture. There's a separate unit for the software lab, and there are two that are in the lab right now, the one for Neolison and the one for McDonald. And all of these units are being monitored. They're all accurate, stable, and meet the SGSLR requirements and continue to. The optical bench design has changed somewhat slightly than what we may have shown previously. There is an upper bench now that houses the laser and part of the transmit path. As always, as we've always presented this, we are using common optics. The laser light that goes out traverses the same path through the telescope as the satellite returns coming back. This is a 50 centimeter diameter telescope primary mirror, and we use aperture sharing so that most of the light that returns uses most of the light that returns uses most of the primary mirror. The light coming back then takes the receive leg and goes through the receiver, and we also have a star camera leg to do star calibrations. Our current laser is the photonics industry laser, the RGL 532. We have not had as much success in terms of reliability with this laser or the photonics industry laser that we had purchased prior to this. They both had to go back at least a couple of times for repairs to the manufacturer after only a short period of time using. So we are back to investigating the possibility of finding another laser. KBR is in discussions right now with Bright Solutions on potential of modifying their one of their COTS products to meet our requirements. In terms of the meteorological instrumentation, we have made a decision on make and model for everything except for the sky camera. We have procured all of the MET4As that we need, parascientific MET4As, and we have them in-house and have tested them. All three of our shelters for all three of the first systems are built. On the lower left, you see the shelter at GGAO at Goddard. That was built by the Goddard Facilities Group. The middle picture shows the shelter at Neolison that was built by the Norwegian Mapping Authority, and on the right is the shelter at McDonald Observatory that was built under contract to KBR. And I also want to point out that, as you can see, there are three Botter Planetarium domes, the 4.2 meter domes that have been installed, as you can tell, and have passed the acceptance testing and are functioning. The software is making good progress. We've demonstrated tracking following a schedule, simulated tracking of satellites, and simulated star calibrations by using software simulators that were developed by the manufacturers of the hardware. The software has also been tested with some of the actual hardware. We have had a portion of the operational ranging software that was tested with the gimbal and mass simulator and the dome. And then we have the ranging control electronics, the time and frequency, and the MET4 in the software lab, and have been used with the software. The preliminary operator interface is currently in use during our testing, and it's basically ready to start INT. We call it RAT GUI. It stands for the Remote Access Terminal Graphical User Interface. This slide shows an example of the RAT GUI displays. This screenshot was courtesy of Randy Rickliffs, who is the developer of the software package. The flow diagram here shows our basic process to get from where we currently are, which is in the middle or near the end, really, of for some of the subsystem builds, all the way to operations. So we will be entering integration and testing at the SGSLR shelter very shortly, within a few months. Once that's over, completed, and we're satisfied with the testing of all the systems together, we will go into pre-verification, where we're doing a lot of satellite laser ranging, star calibration, ground calibrations to make sure that the system is ready, works properly, and meets the requirements that we can see, and is ready for verification. We go into verification. Before we do, we have to freeze the hardware and the software, and during that period of time, we can't basically touch anything. At the end of that, we have a pre-ship review for the Neolison system. We will be presenting to the Norwegians for their acceptance. We will ship, and then we begin operations. Verification for us is basically co-location. NASA's been using co-location of two systems for decades, very successfully. The last one we did was for NGSLR, the prototype for SGSLR. So we will be doing simultaneous ranging with Mobla 7 throughout the period of verification. The ranges, the simultaneous ranges, are then one is transformed to the origin of the other system, and they can be compared directly. Once we deploy and it reaches the Neolison, and we install, we'll be doing a testing to make sure that the performance is good. Once we are convinced that things are working properly, we will begin the first operational satellite tracking there. We expect to be collecting the data and sending it into the ILRS during the quarantine period. At the same time, we'll be training so that the Norwegian Mapping Authority can take over. And then at the end of this period, we'll go through an operational readiness review and hand the system over to NMA. This does not mean that we are abandoning them at that point. The NASA team will continue software development, maintenance, and upgrades during commissioning and throughout operations, just like we will do for all of the SGSLR systems in the NASA family. And then finally, Neolison deployed in 2024 and starting operations in early 2025. The next system to follow will be the McDonald Observatory in Texas, followed by one or the other of GGAO in Maryland or Hawaii at Haleakala. Those two will be next in some order. And then the plan is to replace the rest of the legacy SLR network, NASA's legacy SLR network, over the next decade, at what we expect to be approximately one per year. Thank you. That's it. Questions?
Right here, Toshi.
John, first of all, it's wonderful to see you even remotely, and great to hear the progress. My question is the environment. In such a low temperature or maybe special environment, do you need to take any measurements, special measurements for this site?
For the Neolison site,
Yes.
you're asking?
Yes.
So the measurements that we're going to be taking are in terms of are the same. We will obviously be doing ground calibrations, and the Norwegian Mapping Authority is monitoring the stability of the site, so maybe that's a separate measurement.
Dan?
My question is any special how to say things to be considered for low temperature. I mean, you have to operate. Yeah, that is my question.
Okay, so we have special requirements on for all of the systems that they have to be able to operate at very low temperatures and very high temperatures as well. This is actually one of the reasons why we've had some issues time-wise getting the telescope to conform to that. It's still not quite doing, the current system is still not quite capable of spanning the whole range, but they are capable of hitting a section of that range. So for the cold temperatures, we should be fine. There's a requirement, like I said, for all of the outside equipment, including the dome is not going to be heated, so all of the outdoor equipment has to be able to handle that temperature range. Did that answer your question?
Yes, that was good. Thanks, Jen.